All right, let's talk about gravity for a minute. Gravity is a force, and we've learned a couple of expressions for the force of gravity. One of them is the force of gravity is equal to the mass times little g. So Fg is the force of gravity, also known as weight of an object, and is measured in newtons, as all forces are. M refers to the mass measured in kilograms. And G is an often confused symbol. A lot of people call it gravity, but it's not gravity. G stands for the gravitational acceleration. In meters per second squared, or sometimes is referred to as the gravitational field, in newtons per kilogram. One of the ways that we can find this equation is if we were to take and collect some data on the weight of an object, force of gravity in newtons, versus the mass of an object measured in kilograms. When we graph this, we would find a nice linear relationship. The force of gravity is proportional to the mass, and the slope of this graph is in fact what we call little g. So for objects near the Earth's surface, little g, the gravitational acceleration or the gravitational field, is about 9.8 meters per second squared. Or sometimes to make the math easier, we'll just go ahead and round that to a nice even 10 meters per second squared. We also learn from Newton's Law of Universal Gravitation that the force of gravity Universal Law of Gravitation, that the force of gravity is a force of attraction between any two objects that have mass, and can be found by this simple formula. Big G times the mass of object 1 times the mass of object 2 divided by r squared, where r is the distance between the centers of the two objects. And big G is the universal gravitational constant, which is equal to 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. So here let's take force of gravity equals mg, and force of gravity equals big G, m1, m2 over r squared. Let's set them equal. mg equals big G, m1, m2 over r squared. Now, here we're talking about the weight of an object. Say we have an object near the Earth's surface. So this is the mass of the object and the acceleration of gravity near the Earth's surface. This would be big G, the universal constant, mass of the object, mass of the Earth, divided by r squared. Remember, r in this formula is the distance from center to center. So for an object near the Earth's surface, that would be basically the radius of the Earth. So in this formula, we've got the mass of the object, mass of the Earth, over radius of the Earth squared. Notice the mass of the object will divide out, and we will get a nice expression for the acceleration of gravity. It's big G, mass of the Earth, over radius of the Earth squared. That formula can be applied to any celestial body. For the moon, just use mass of the moon, radius of the moon. For Jupiter, mass of Jupiter, radius of Jupiter. Let's take a few minutes and talk about universal gravitation and Kepler's laws. Newton's law of universal gravitation says that the force of gravity between any two objects that has mass is equal to the constant big G times m1 times m2 divided by r squared, where r is the distance between the centers of the two objects. Now, Kepler came up with three laws. His first law is that orbits are ellipses, not circles. His second law is the law of areas, that says a line will sweep out equal areas in equal times. A line joining the planet and sun would sweep out equal areas in equal times. And Kepler's third law is a quantitative relationship that t squared over r cubed is equal to t squared over r cubed. For any two objects that orbit the same central body, the ratio of period squared to orbital radius cubed is going to be the same. So we're going to see how Newton's law actually shows us a quantitative way of calculating using Kepler's laws. But let's look at Newton's law here first. There's a couple of things that we can find out. If we presume that orbits are circular, say we have a satellite orbiting a small satellite orbiting a large central body. That could be a planet around the sun, it could be a moon around the Earth, it could be a satellite or a spacecraft around the Earth or around the moon or something like that. So small satellite orbiting a large central body. Then we know that the net force acting on that object, that satellite, is equal to mass times acceleration. Well, the only force acting on that object is the force of gravity. So I can say G, I'll use big M for the central body and little m for the satellite, over r squared is equal to the mass of the satellite times the acceleration of the satellite. Now, if it's moving in a circular path, the acceleration will be v squared over r. Now, in this equation, we see two different r's. Sometimes that's going to be the same r, and sometimes it's not. On the left side, in Newton's law, the r represents the distance between centers of the two objects. In the right side, v squared over r, the r represents the radius of the circular path. And as we can see, in the case of a small satellite orbiting a large central body, the distance between centers will in fact equal the radius of the circular path. So in the case of a small satellite orbiting a large central body, small satellite, large central body, then the r's are the same. And so this r, I can multiply both sides by r. I can also cancel out an m. That leaves me with g times the mass of the central body over r equals the m divided out, the r canceled out, equals v squared. And so the speed of a satellite can be found by taking this formula. Square root both sides. G, mass of the central body, over r equals the speed of the satellite. So I can get the speed of the satellite that way. I can also, assuming the same situation, I can also look at the period of a satellite, the time it takes to complete one orbit. I know that if it's moving in uniform circular motion, that speed is equal to distance over time, which would be 2 pi r over the period. So v squared is going to be 4 pi squared r squared over t squared. Then if I take and divide both sides by r, so v squared over r would just be this divided by r. That's going to cancel out one of those r's. So 4 pi squared r over t squared. So v squared over r is the same thing as 4 pi squared r over t squared. So let me back up to this equation here, where I've got big G, mass of the central body, mass of the satellite, over r squared is equal to mass times acceleration. And the acceleration v squared over r is the same thing as 4 pi squared r over t squared. I'm going to start with this on a new sheet of paper. Let's grab that. So what I've got then here is I've got g m over r squared equals m times 4 pi squared r over t squared. And at this point I can see I can divide out the mass of the satellite, disappears. So that's going to leave me with g big M over r squared equals 4 pi squared r over t squared. Now I'm going to clean this up just a little bit. I'm going to bring the t squared up here. So t squared. I'm going to bring the gm down here. So the gm and the t squared are going to switch places. I'm going to bring this r over here, divide both sides by r to get it down here. That gives me t squared over r cubed equals 4 pi squared over gm. Now, this, in fact, is a mathematical statement of Kepler's third law. Remember, Kepler's third law said that t squared over r cubed is equal to t squared over r cubed for any two objects that orbit the same body. So what we can see here is that t squared over r cubed is equal to, we have a constant times a constant, divided by a constant times mass of the central body. And that's why for Kepler's laws it had to be two objects that orbit the same central body. So basically what we have is t squared over r cubed is equal to a constant for any objects that orbit the same central body. And this is a statement of Kepler's third law. I can use this result to calculate things like the mass of the sun. So if I know the period and the orbital radius of an object that orbits the sun, I can use this formula to calculate what the mass of the sun is. Remember, m here in this formula is the mass of the central body. I can also use this to calculate things like the period of a satellite or the orbital radius of a satellite, those types of things as well. But that's basically how you derive Kepler's third law, by looking at Newton's laws, his law of universal gravitation and his second law of motion. So when you encounter a satellite problem, a lot of times the way you begin is to look at F equals ma. The net force equals mass times acceleration. You have your force of gravity. You have your force of gravity equation. You set it equal to ma. You know that if it's circular, you've got the acceleration as v squared over r, and then you can simplify from there, solve for the speed, or you can simplify from there, solve for the period. We can get an expression for the period, in fact, by using this one right here. It's pretty easy to do. If I want to solve this for the period, I would say, okay, so that means that t squared equals 4 pi squared r cubed over gm, and then I simply square root that to get the period. Square root of 4 pi squared r cubed over gm, all of that in the square root. That is the period of a satellite. And so again, easy to do. I start with Newton's laws. I can work my way to either the speed of the satellite or the period of the satellite, or I can use this relationship. I can find things like the mass of the central body and things like that. Another way to approach satellite problems is the conservation of angular momentum. And let's just do a quick reminder. Angular momentum there are two ways to find angular momentum. There is the symbol we use is L for angular momentum. There is I omega for a rotating object, or R perpendicular mv for a linear moving object. So if I have a satellite in an elliptical orbit, okay, let's call this R1, and let's call this R2. We'll call this V1, how fast it's moving here, and V2, how fast it's moving here. So this is our central body here, and this is our small satellite in this elliptical orbit. Now, angular momentum is conserved when the external net torque is 0. When there's no outside net torque, then angular momentum is conserved. So, in the case of a satellite, the only force acting on the satellite is the force of gravity. And that force of gravity passes right through the axis of rotation. Therefore, there is no torque produced by gravity. Therefore, there is no external net torque, which means that angular momentum is conserved. And so, I can do angular momentum at position 1 for the satellite is equal to angular momentum position 2 for the satellite. And because I've got an object moving in with a linear velocity, I'm going to use this rmv. Notice the velocity vector is in fact already perpendicular to the radius, so r perpendicular mv simply becomes rmv. So L1 is going to be r1, mass of the satellite, times v1. Now will equal r2, mass of the satellite, times v2. And so as you can see, the mass of the satellite will divide out, and I'm left with r1 v1 equals r2 v2. And this can then be rearranged and solved for V2 or for R2 or for any of these can be solved for by using conservation of momentum. So there may be a problem that says if at position 1 the speed is V1, what is the speed of position when it's at position V2? And so if I'm looking for the speed at V2, I would simply divide it, and I would say, hey, look, R1 over R2 times V1 is equal to V2. And there I've got, using conservation of angular momentum, I'm able to solve for the speed of the satellite.